Chapter 6, Bending, Part C, Shear and Moment, Example 4. In this example, just consider we have a two simple support uh, beam handling a distributed load of W of 120. We want to calculate maximum moment on this beam configuration. So length is 112, W is 120 pound per feet, and let's develop a summation of forces at y that gives us Ra plus Rb. It's a equal to a half of 120 times the length of beam, which is a 720 pounds. So that's a half of load times length, and that's 720. And that 720 is distributed between Ra and Rb. And because more chunk of the weight is closer to support B, we have an intuition that support B goes with the bigger amount of force. So reaction RB should be at least a little bit higher than RA. In this case, it's something more than that. So, and at the same time, if we just convert the distributed load of of W with a 700 one concentrated load from one third from 12, it's 4, and this is 8. One third from base, it's 4 meter, one third of 12, and this is 8 meter. Sorry, 8 feet, 4 feet. And by just developing the moment about, for example, point A, it just and is a counterclockwise considering as a positive moment, and it gives you RB times 12, RB times the whole length, which is the consistent with our counterclockwise direction, that's a positive, minus 720, a concentrated load of uh, convert a distributed load to a single load from the distance from support A, which is 8 feet. So it just gives you RB 480, and if that's 480, RA, it just goes by 240. As we discussed already, RB here is twice as RA. So as soon as we know what RA and RB is, we can develop our shear diagram. We climbs by the amount of RA at the beginning of shear, then we just climbs down. Mhm. This is linear, this is second degree, and at the very end we just climb by the amount of our support, which is RB 480. So because we are reaching zero here, we need to be at negative 480. The next step is to find where the shear moment meets the x-axis. So that's finding x. Mhm. So x is the distance in which shear goes zero. Mhm. That's where shear meets the horizontal axis. If you look at the W diagram more carefully, it just gives you from W diagram intensity of distributed load is if you divide the your W by the length, it just gives you the intensity. 120 over the length of beam AB gives you a 10, and that's the intensity. So 240 shear at the beginning minus there I have 240, and where it the effect of distributed load on shear cancels that 240. If we just consider that's a 10x, if we travel by the length of x, this is x, this is this intensity times length. Uh-huh. And if we want to calculate the area under load, which is shear, and we had 240 at the beginning of shear, minus the area under load, which is shear until the, uh, reaching x, that's a half of 10x times x. That's a half of 10x times x. And you solve it for x, it gives you x is equal to 6.93 feet. Mhm. As soon as we calculate x, we can just calculate the area under shear to get the maximum moment. So the approach for getting the maximum moment, which we were looking for from the beginning, is solution one. We can get it from drawing. So for example, a blue dashed area, which is this part, is the amount of maximum shear. So if we know from a parabolic spandrel, which is this one, and if that goes by a 1/3 of BH, it just goes by 2/3, because the whole should be the overall the two area with each other consist a rectangle with the B and H. If this is B and this is H, so if this is 1/3, the other half should be 1/3. So the our area is 2/3 of B times H. So if you proceed to solve that, it just says 2/3 of 6.9. We already calculate the numeric value times the height, which is 240, the initial shear, and that gives you 1,109 pound-feet. You can also solve this, get the moment from the mass directly. And how is that? If you just develop the summation of moment about x goes zero, and we do that's not zero because that's a somewhere in the middle. Definitely there is an internal moment because we cut the beam through. And so this, if you do the math, is the you develop this equation, summation of the effect of moment up to that point should gives you a numeric value. That numeric value is just represent moment at x, which is again a 1,109 pound-feet. Mhm. In the in the other example, we can have a cantilever beam with a length of 4 meter with two loading, a distributed load of W of 1.5 kilonewton per meter and a concentrated of 2 kN at the free end A. Mhm. If we want to develop or create the shear and moment for this example, likewise, a just summation of moment about this time, free end goes by zero. So converting again distributed load to a concentrated load of 1.5 times 2, it's a 3. So this is the positive, counterclockwise is positive, about point A, that's a 3 times a distance of 3. Mhm. Plus a 5. Mhm. Which is RB. RB should cancel out this, the effect of distributed and the concentrated, which is 5. Time what? Time total length. And minus MB, there is an MB there with the counterclockwise direction that goes 0. Mhm. And that gives you MB is equal to 11 kN. Mhm. If you want to draw the shear diagram, it just a step down at A, and because there is no loading from A, for example, to if you call it C here, so no load, it means there is no slope for V, so that's a constant line. And then there is a distributed load, so there is a linear drop down, and then the area under load is the change in shear. So that's a3. That's a change is a numeric value of 3. Mhm. And if we want to develop the moment from that, so that's constant. This is 1 degree. And if you develop the moment, it just goes from a constant line to a linear moment. And then this is 2nd degree, so moment should be definitely the 1st degree. As you can see here, the numeric value of numeric value, absolute numeric value, forget about the direction. Absolute numeric value of shear is increasing. The slope of moment should increase, which is increasing. So it is increasing to reach to the moment of MB11. And that's all for reviewing of drawing of shear and moments. Thank you.